Today we are explaining the paper AVO Agentic variation operators for autonomous evolutionary search.
Can we start with the big picture of what this paper is trying to do?
The paper turns evolutionary search into an agent-driven coding loop. Instead of relying on fixed mutation rules or a single language model generation step, it lets an autonomous agent inspect old kernels, read documentation, edit code, run benchmarks, and repair mistakes on Blackwell attention kernels. That process speeds QDNN by up to 3.5% and flash attention by up to 10.5%, then adapts the result to grouped query attention in about 30 minutes.
What was still broken in earlier language model-assisted evolutionary search?
Earlier systems still kept the model inside a rigid framework sample parents, ask for one candidate, then evaluate it from the outside. That makes the model a proposal generator, not the search operator itself. It cannot decide on its own when to inspect a past version, run a diagnostic, consult reference code, or keep debugging until a hardware bottleneck is understood.
So what exactly changes once they introduce AVO?
The key design change is shown here. On the left, the framework owns sampling and evaluation, and the model only emits code once. On the right, AVO makes the agent responsible for the whole variation step, so it can use the current lineage, reference kernels, profiling tools, and persistent memory before it proposes the next committed kernel.
What happens inside one variation step once the agent turns the whole loop?
A single step becomes a small autonomous engineering session. The agent plans an edit, implements it, evaluates correctness and throughput, fixes bugs if needed, and only commits a new version when it passes the checks and matches or beats the best score so far. In this paper, each candidate is a QDA attention kernel, so the scoring function rewards both correctness and speed on the target hardware.
Why is that setup better than a fixed sample and generate pipeline?
Because the search can stay with a promising idea long enough to test it properly. Over the 7-day run, the system explored more than 500 optimization directions internally, but only 40 successful versions were committed. The lineage keeps useful context for later steps, and the supervisor only intervenes when progress stalls, so the main agent can keep revisiting and refining ideas instead of guessing once and moving on. Now let us move to the main multi-head attention benchmark.
What stands out most in this multi-head attention chart?
The strongest story is on causal attention. AVO beats both baselines at every tested configuration now, with gains from 0.4 to 3.5% over QDNN and from 5.0 to 10.5% over flash attention on non-causal attention. The picture is more modest. The gains appear mainly at the longer sequence lengths, while the shorter settings stay close to measurement noise. So the paper is not claiming a universal blowout. It is showing a clear win on the harder, causal side in competitive results elsewhere. The paper then checks whether those improvements survive a different attention pattern.
What does this grouped query attention result prove?
It shows that the discovered optimizations are not locked to one exact benchmark. After evolving the multi-head attention kernel, the agent adapted it to grouped query attention in about 30 minutes with no human guidance on the code changes. Across all grouped query configurations, on causal grouped query attention, the gain reaches 7.0% over QD and 9.3% over flash attention on non-causal grouped query attention, it reaches 6.0% over QD and 4.5% over flash attention Next, let us look at how the long autonomous run actually progress.
What should we read from this evolution trajectory?
The curve does not drift upward smoothly. It jumps, then plateaus, then jumps again. That matters because it means the big gains came from a few architectural changes rather than from random incremental noise. The paper says the 40 committed kernels are only the successful visible path. Behind them, the agent explored more than 500 directions. The biggest inflection points came from branchless accumulator rescaling, overlap between correction work and matrix multiply work, and a register rebalance across warp groups.
Which of those three changes matter most?
The paper highlights 3 representative wins. Branchless accumulator rescaling with a lighter fence is the biggest single jump. Overlap between correction work and matrix multiply work removes idle time. Register rebalancing reduces local memory spills in the correction path.
Why does the branchless rescaling help so much?
In the old kernel, online softmax rescaling used to branch every time it checked whether the running maximum had changed. That branch edit synchronization overhead and blocked the use of a lighter fence in the correction path. AVO switched to a branchless design that always computes the factor and selects one when rescaling is unnecessary. That removes warp divergence, makes the lighter Nundle bank fence safe, and produces the paper's largest single gain, 8.1% on non-causal attention and 1.6% on causal attention.
What changed in the overlap step?
The kernel processes to query tiles in parallel, and each one needs a product value matrix multiply followed by correction warp normalization. Before version 30, the correction warp waited until both matrix multiplies finished, so it sat idle through the second one. AVO changed the schedule so normalization for the first tile starts as soon as its matrix multiply finishes, overlapping that work with the second multiply. That turns a serialized handoff into a pipeline and adds 1.1% on non-causal attention and 0.4% on causal attention.
And why did register rebalancing help?
Blackwell gives each streaming multiprocessor a fixed 2048 register budget across warp groups. The inherited split gave the correction warp only 80 registers, so it spilled values into slower local memory while the softmax group still had headroom. AVO moved the allocation from 192, 80, and 48 registers to 184, 88, and 56. That small shift cut spills on the critical correction path and added to 0.1% on non-causal attention, while causal attention stayed roughly flat.
What does all of that say about Agentic switch overall?
The important point is that AVO is not winning by writing code once and hoping for the best. It reads documentation, profiles bottlenecks, tests hypotheses, and only keeps verified improvements. The paper's 3 case studies span synchronization, pipeline scheduling, and register allocation, so the evidence points to real hardware reasoning rather than superficial code churn.
Can you give me the one-sentence takeaway before we close?
AVO makes the agent itself the variation operator, and on a kernel problem that already gets months of expert tuning. That change was enough to find verified optimizations that beat QD and unflush attention for and then transfer quickly to grouped query attention.
So the contribution is both the new search operator and the proof that it can discover hardware level wins.
Exactly. That is the main idea, the evidence, and the reason this paper matters.